systems of linear equations, solving using the elimination method or addition method. So yet another method for solving the same type of system, systems of two linear equations, is called the elimination method, and it's also referred to as the addition method. With a little bit of practice, this can be the quickest method, and a lot of times the method most students prefer. So step number one is we have to make sure each equation is written in standard form. Ax plus by is equal to c. Look at example 1, that's exactly what we have. Nice neat columns for the x's, for the y's, and for the constants. So then what we want to do is identify or look at the coefficients for the x's and y's, and our goal, or what we need, is opposite coefficients for the x's or the y's. In other words, opposite numbers. So if you look at the x's here, positive 15 and positive 28, certainly not opposites, and we'd have to do quite a bit of work to get them to be opposite numbers. However, the y's are already opposite numbers, positive 24 and a negative 24. So step number 2 is already done for us. So what we're going to do is add these two equations together. That's why it's referred to as the addition method. And when we do that, the variables with the opposite coefficients, the y's in this case, cancel out. Hence, the elimination method. So even though the y's cancel out, we still have a linear equation, but a linear equation with only one variable to solve, and a pretty simple one at that. We can easily solve for x. X is simply equal to 1. Now we just have to go back and find y, and we do that the exact same way as we did in the substitution method. Take this value and substitute it back into one of the original equations. If I plug it back into the first, 15 times 1 plus 24y is equal to negative 33. Allow me to solve for y. Y works out to be negative 2. So we found x, we found y, and still keeping in mind what these values actually are. It's a point on the graph. If we were to graph those two equations, those two lines would intersect at the point 1, negative 2. Example 2. Solve using the elimination or addition method. Take a quick check, make sure the equations are in standard form. They are. And in this case, step number 2 is not done for us. We need to come up with opposite coefficients for either the x's or the y's. So you always want to look at both sets of coefficients. A lot of times it'll be easier to eliminate one over the other. Now in this particular case, it's pretty much the same amount of work either way. So I'm just going to go ahead and eliminate the x's. One's already positive, one's negative, but they're certainly not the same. So we want to find the least common multiple for 8 and 2, the coefficients for x. Well, the smallest number that both 8 and 2 would divide into is, of course, 8. So we want one coefficient to be positive 8, the other one to be a negative 8. Well, the first one already has a positive 8 for the coefficient, so the first equation is not going to change. We're going to leave it the way it is. That means the second coefficient for x, we want it to become a negative 8. It already is a negative 2, which means we have to multiply it by 4. Multiply the entire equation by 4, which gives us negative 8x plus 36 y is equal to 32. Now that we have opposite coefficients for the x's, we're going to add the two equations together. The x's eliminate, leaving us 33y is equal to 66. A real simple linear equation that we can easily solve for y. Y is equal to 2. Now take this value and substitute it back into one of the original equations. If I substitute it back into the second, negative 2x plus 9 times 2 is equal to 8. Then all I have to do is solve for x. X works out to be 5. So once again, the solution to this system, the point 5, 2. One point of intersection, one solution to the system. Example 3. Solve using the substitution, or excuse me, solve using the elimination method. As we can see, step number 1, these are not in standard form. So the first thing we need to do is get them into standard form. The first equation in standard form is going to be 4x plus 6y is equal to negative 20. The second equation, 6x plus 13y is equal to negative 48. So now we have them in standard form. We look at the coefficients for the x's, look at the coefficients for the y's, and the coefficients for the x's are a little bit smaller numbers, so they should be a little easier to work with. 4 and 6, so we want to find now the least common multiple for 4 and 6, which is 12. We want one coefficient to be a positive 12, the other one to be a negative 12. It doesn't matter which is which. If I make the first one the positive 12, that means I have to multiply the entire first equation by 3. The second equation becomes a negative 12, so I multiply it by a negative 2. So the first equation becomes 12x plus 18y is equal to negative 60. The second equation, negative 12x minus 26y is equal to 96. Add the two equations together. The x's eliminate, leaving us negative 8y is equal to 36. So y is equal to negative 9/2. We solve for y. Go back now and solve for x. I'm going to substitute this into the first equation here. 4x plus 6 times negative 9/2 is equal to negative 20. And solve for x. 4x minus 27 is equal to negative 20. So x works out to be 7/4. So one solution once again, the ordered pair 7/4, negative 9/2. And example 4. Solve this system of two linear equations using the elimination method as well. Step number 1 is already done in this case. So step number 2, determine which variable you want to eliminate, the x's or the y's. It's about the same amount of work regardless, or it actually is the exact same amount of work, as you're going to see here in a minute. But either way, whether you try to eliminate the x's or the y's, you'd end up multiplying the entire first equation by negative 5, which would give us negative 10x minus 15y is equal to negative 65. And of course the second equation would remain the same, 10x plus 15y is equal to 26. So now when we add the two equations together, what happens is both the x's and the y's eliminate. So if they both eliminate, we're left with 0 on the left hand side. The right hand side becomes negative 39. So same thing as the substitution method. If all the variables cancel, that means one of two things: infinitely many solutions or no solution. The remaining equation here is obviously a false statement, which means no solution to this system. Therefore, the lines are parallel. If you were to graph those two lines, graph those two equations, the lines would never touch or intersect.